In Digital 2 of the UCanDo series, you saw how numbers were added together in circuits referred to as adders. You learned about the half adder and the full adder devices. Now you will learn how numbers are subtracted from one another. We will begin our study of subtraction by examining the complement of a binary number. The complement of a binary bit is nothing more than its inverse status. In other words, the complement of 1100 would be 0011, or the complement of 1010 would be 0101. As you can see, to make the complement of any binary number, you simply change all the ones to zeros and all of the zeros to ones. The first method of creating a complement number is often referred to as ones complement. As you shall soon see, we can subtract any number by adding its ones complement in a certain way. As you recall, the rules for binary addition were simple. They were 0 plus 0 equals 0, 1 plus 0 equals 1, 0 plus 1 equals 1, and 1 plus 1 equals 0, carry 1. And the rules for binary subtraction were equally as simple. 0 minus 0 equals 0, 1 minus 0 equals 1, 1 minus 1 equals 0, and 0 minus 1 equals 1, borrow 1. The alternate method of binary subtraction involves the use of ones complement. To better understand how the ones complement works in subtraction, we will demonstrate with a couple of examples. In the first example, we will start by subtracting decimal number 3 from decimal number 5. 5 will become the minuend, and 3 will become the subtrahend. First, we must convert the minuend and subtrahend into their binary equivalents. Next, we change the subtrahend into its complement number. This changes the binary 3 into 100. Then we simply add the numbers together. We know that 1 plus 0 equals 1. 0 plus 0 equals 0. And 1 plus 1 equals 0, carry 1. Next, the one bit that was carried is added to the least significant bit to the total sum. When we do this, we see that the answer is 010 in binary, or 2 in decimal. This time we will subtract decimal 6 from decimal 14. As you can see, the binary equivalent of decimal 14 is 1110, and the decimal equivalent of 6 is 0110. First, we find the complement of the subtrahend. Then we simply add the complemented subtrahend to the minuend. You already know that 0 plus 1 equals 1. 1 plus 0 equals 1. 1 plus 0 equals 1. And 1 plus 1 equals 0, carry 1. Next, we add the carry bit to the least significant bit. 1 plus 1 equals 0, carry 1. 1 plus 1 equals 0, carry 1. 1 plus 1 equals 0, again carry 1. And 1 plus 0 equals 1. When binary number 1000 is converted into decimal, it equals 8, which is the answer to our problem of 14 minus 6. Another common complement method is called 2's complement. In the 2's complement method, the subtrahend is complemented by changing the zeros to ones and the ones to zeros, just as we did in 1's complement, but this time the extra 1 is added to the subtrahend before it is added to the minuend. The last carry product is then omitted. In this example, we will subtract 9 from 12. First, you must find the complement of the subtrahend. Next, you simply add 1 to the complement's value. Then you add the 2's complement value to the minuend. 0 plus 1 equals 1. 0 plus 1 equals 1. 1 plus 1 equals 0, carry 1. And since we carried 1, we now have 1 plus 1 equals 0, carry 1. Since we had already added 1 to the subtrahend, we discard the carry bit, and our answer becomes 0011, or 3 in decimal. Next, we will examine the multiplication process used in microprocessor-based systems. Microprocessors are designed to perform addition problems at an extremely fast rate. The microprocessor can also be programmed to multiply by performing a series of successive addition steps. We will now examine one such circuit. Here we see a simple 4-bit binary multiplier using the successive addition process. Notice that the multiplicand is placed on the A inputs of the 4-bit parallel adder stage. Also notice that the multiplier is nothing more than a down counter which controls the add enable input. The sum of inputs A and B are placed into an accumulator. The total in the accumulator is then fed back into the B inputs of the 4-bit parallel adder stage. And notice that the symbol used to represent the sum output is the Greek letter sigma. Now let's examine this circuit and see how it works. We will start by multiplying 3 times 4. As you may have noticed, the multiplicand has been loaded with the number 4 in binary, and the multiplier, which is in the down counter stage, has been loaded with binary 3. The accumulator has been cleared and is set to 0, 0, 0, 0. Since the multiplier has a binary number greater than 0, 0, 0, 0, it will enable the 4-bit parallel adder stage and cause it to add the binary numbers placed at inputs A1 to A4 with the binary numbers placed at inputs B1 to B4. You may have also noticed that a multiplier decreased by 1. Since the inputs A1 to A4 have a binary 4 and the inputs B1 to B4 have a binary 0, the accumulator will store the sum of binary 4. Next, the multiplier again decreases by 1, which in turn enables the adder stage to add the inputs of A1 to A4 with the inputs of B1 to B4. At this point, inputs A1 to A4 have a binary value of binary 4, and inputs B1 to B4 also have a value of binary 4. Therefore, the accumulator will store this sum as a binary 8. At this point, the multiplier will once again decrease by 1 and enable the adder stage, causing it to add the inputs A1 to A4 to that of B1 to B4. When the adder stage adds the 4 from the multiplicand with the 8 from the accumulator, the new sum will be 1100 or binary 12. When the down counter reaches 0000, it will no longer enable the adder stage, and the problem is completed. As you can see, multiplication can easily be achieved by using the successive addition process. Division can also be achieved by using a similar process, but instead of adding the values at inputs A1 to A4 with those of inputs B1 to B4, they are subtracted from one another in a successive process. Every microprocessor contains an ALU, or arithmetic logic unit, where the arithmetic and logic operations take place. The variety of operations handled by the ALU will depend on the type of arithmetic logic unit used. Here we see the SN74181 integrated circuit. It is a high-speed arithmetic logic unit that has a complexity of 75 equivalent gates in a 24-pin monolithic IC package. This IC performs 16 binary arithmetic operations on 2 4-bit words. One 4-bit word is placed at inputs not A0 to not A3, and the second 4-bit word is placed at inputs not B0 to not B3. The operations performed by this IC are selected by the 4 function select lines S0, S1, S2, and S3. When performing arithmetic manipulations, the internal carrier must be enabled by applying a load to the mode control input labeled M. A full carry look-ahead scheme is made available for fast simultaneous carry generation with a group carry propagate labeled not P and a carry generate labeled not G for the 4 bits in the package. The pin labeled CN is the carry-in input, and the pin labeled CN plus 4 is the carry-out output. The pin labeled A equals B is a comparator output, and the pins not F0, not F1, not F2, and not F3 are function outputs. The ALU works in conjunction with a number of registers which are used to temporarily store data and with a control circuit used to control the ALU. You will learn more about the arithmetic logic unit when you study microprocessors. We will now pause for a short review of the material just discussed. The complement of a binary number is its reverse bit status. For example, the complement of 1110 would be 0001. There are two types of complement numbers, 1's complement and 2's complement. To find the 1's complement of a number, you simply find the complement of the subtrahend, then add the complemented subtrahend to the minuend. Then you add the carry 1 to the least significant bit of the sum. This method is used by digital circuits for subtracting binary numbers. 2's complement is very similar to the 1's complement in that you must find the complement of the subtrahend, then you add 1 to the complemented subtrahend before it is added to the minuend. The last carry digit is then omitted. Every microprocessor contains an ALU section where the arithmetic and logic operations take place. ALU stands for Arithmetic Logic Unit. This concludes our first review. Next, we will examine multiplexer and demultiplexer circuits to see how they work. The digital multiplexer is a combinational logic circuit containing 1 to 4 control inputs and 2 to 16 data inputs for each data output. Some multiplexers even provide complemented data outputs. Basically, the digital multiplexer performs the function of a single-pole multi-position switch in which one of the data inputs will be connected to the output at any one time. The particular data input being selected is controlled by the control inputs line. Digital multiplexers are used when a selection must be made from several data sources and the information must be routed to one destination. This method of selection is often referred to as data routing. Here we see the equivalent circuit of a 4-input multiplexer containing 2 control inputs with 1 true output and 1 complemented output. To better understand the digital multiplexer circuit, we will examine this simple equivalent circuit. The 4 different data sources are applied at inputs I0, I1, I2, and I3. The control inputs are applied at S0 and S1. The outputs are taken from the complement output and the true output. In our example, we will assume the data is being applied at all 4 inputs. When control inputs S0 and S1 are low, we see that a high signal is being applied to all 3 inputs of AND gate A, which causes AND gate A to turn on with the data. AND gates B, C, and D will remain off. When AND gate A turns on, it causes OR gate E to also turn on. The OR gate then feeds the information into both outputs, true and complement. When control input S0 is made high and control input S1 remains low, we see that AND gate B turns on while AND gates A, C, and D remain off. When AND gate B turns on, it causes OR gate E to also turn on and transfer this data information from input 1 to the true and complement outputs. When control input S1 is made high and control input S0 is made low, we now see that AND gate C turns on, while AND gates A, B, and D remain off. AND gate C causes OR gate E to turn on and transfer the information to the outputs. When both control inputs S0 and S1 are made high, it causes AND gate D to turn on while AND gates A, B, and C turn off. Once again, OR gate E is turned on, and the data information from input 3 is transferred to the complement and true outputs. As you can see, by controlling the high-low sequences on control inputs S0 and S1, this circuit can be made to read any one of the 4 data lines at any time. Oftentimes, the multiplexer circuit is abbreviated as MPX or MUX. Here we see the SN74150, which is a 16-line to 1-line digital multiplexer IC. This integrated circuit contains 16 6-input AND gates, one 16-input NOR gate, and 9 inverter gates. The SN74150 is capable of multiplexing 16 data lines into one output. A 4-bit code placed at the data select lines, which are used as the control lines, will determine which of the 16 input lines are to be routed to the output. The strobe input is used as an override to force the output into its logical 1 state. Since the output of this device comes from a NOR gate, the data is inverted from the input to its output. This IC has a typical propagation delay of 10 nanoseconds with a typical power dissipation of 225 milliwatts. Here you see the SN74151, which is an 8-line to 1-line digital multiplexer integrated circuit. Internally, this IC contains 8 4-input AND gates, one 8-input NOR gate, and 8 inverter gates. You may not have noticed, but this IC has 2 outputs. One output, which is labeled W, provides the true information, and the other output, which is labeled Y, provides a complemented output. 3 data select lines labeled A, B, and C are used to determine which of the 8 input lines is to be routed to the output. This IC has a typical propagation delay of 15 nanoseconds with a power dissipation of 135 milliwatts. Here we see the DM8123, which is a quad 2-input multiplexer IC. This IC consists of 4 2-input multiplexers with a common input select logic and a common output disable circuitry. This IC allows 2 groups of 4 bits each to be multiplexed to 4 parallel outputs. Here we see the logic diagram of the DM8123. Even though this IC contains 4 outputs, its operation is the same as the previous multiplexer circuits just discussed. We will quickly examine this circuit to see how it works. The first thing you may notice about this circuit is the arrow pointing toward the body of each of the OR gates. These are special OR gate circuits which can produce a tri-state output. The output may be high, low, or placed in a high impedance state. When placed in that high impedance state, the devices are effectively removed from the circuit. The arrows may or may not be present on a diagram, but the line will always enter at the side of the symbol. One of the 4-bit inputs will be placed on inputs I0A, I0B, I0C, and I0D. The other 4-bit input will be placed on inputs I1A, I1B, I1C, and I1D. Also notice there is only one select line on this device. Therefore, the DM8123 can only select between 2 sources of inputs. When the enable input is at the logic 0 level, the outputs are conventional TTL. However, when a logical 1 is applied, the outputs assume a high impedance state. Both upper and lower output transistors are turned off. The resulting condition allows many devices to be connected to a common bus line without loading down or being loaded down by other devices on the line. Now let's examine the operation of this circuit. We will begin by assuming that all the data inputs are high or active and the enable input is low. When the data select line is low, inputs I0A, I0B, I0C, and I0D are made active. These AND gates then cause the OR gates to turn on and transfer the data from inputs I0A, I0B, I0C, and I0D to outputs ZA through ZD. And when the data select line is made high, inputs I1A, I1B, I1C, and I1D are made active, resulting in the OR gates turning on and transferring the information to the outputs. As you can see, by controlling the data select line, this IC can transfer bits of information at a time from 2 different sources. Now that you have a basic understanding of how the multiplexer circuit works, we will examine the demultiplexer circuit. Multiplexing was defined as a process in which many data sources may be connected one at a time to one output. Demultiplexing, on the other hand, is the reverse process, or routing data from a single source to various destinations. As you can see from this simple diagram, one input source can be directed to any one of several outputs. The output selected is determined by the control line. To better understand how this happens, let's examine a demultiplexer equivalent circuit. Here we see a logic diagram of a digital demultiplexer circuit. Notice that it looks very similar to the multiplexer circuit we have already discussed. The primary difference is the demultiplexer circuit has only one data input with several data outputs. To better understand the demultiplexer circuit, we will examine how this equivalent circuit works. We will begin by assuming that the data input line is active and that the data select control lines S0 and S1 are low. As you can see, and the gate A is turned on. Therefore, the data from this data input line is routed to output Z0. By making data select line S1 high and leaving data select line S0 low, and the gate B is turned on, allowing the information to flow from the input to the Z1 output. When data select line S1 is made low and data select line S0 is made high, and the gate C is turned on, which allows the data from the data in input to be transferred to the Z2 output. And by making both of the data select control lines high, and the gate D is turned on, allowing the information to flow from the data in input to the Z3 output. As you can see, by controlling the data select lines, the information placed at the data in input can be directed to any one of several outputs, one at a time. Here we see the SN74155, which is a dual 2-to-4 demultiplexer integrated circuit. Internally, this IC contains 8 3-input NAND gates, 2 2-input NAND gates, and 5 inverter gates. The SN74155 is a monolithic TTL integrated circuit featuring dual 1-line to 4-line demultiplexers with individual strobes and common data inputs in a single 16-pin package. The individual strobes can permit or inhibit each of the 4-bit sections as desired. When both strobes are enabled, the common data inputs sequentially select and route the input information to the appropriate output of each section. The data information applied to input 1C is inverted at the appropriate output, while the data applied at 2C is not inverted at the output. The SN74155 has a typical propagation delay of 17 nanoseconds with a power dissipation of 125 milliwatts. Here we see the DM8223 IC, which is a 1-line to 8-line demultiplexer. This IC is TTL compatible. The 8 outputs, 0 through 7, are capable of driving 10 standard TTL loads each. The 3 address lines determine which output receives the data information. The typical propagation delay of this IC is 35 nanoseconds. We will now pause for a short review of the material just discussed. You have seen that the digital multiplexer is a combinational logic circuit which contains 1 to 4 control inputs, 2 to 16 data inputs, and 1 output. However, there are multiplexer circuits available which also provide a complemented output. The multiplexer may be considered an electronically controlled switch in which one of the data inputs is connected to the output. The input information being transferred to the output is determined by the control lines in the circuit. This method of selection is often referred to as data routing. Demultiplexing, on the other hand, is the reverse process, meaning data from a single source is routed to various destinations. The demultiplexers may be considered an electronically controlled switch whereby a single data input line may be connected to any one of several outputs. This concludes review number 2. Next, we will examine register circuits. Registers are nothing more than a storage unit used to temporarily hold information until information is needed. The most common storage register is the shift register. There are several different circuit configurations that are called shift registers. They are classified by the method which data inputs and outputs to and from register. For example, shift registers may be classified as serial in, serial out, serial in, parallel out, parallel in, parallel out, and parallel in, serial out. As you can see, the shift register can convert data from serial to parallel or from parallel to serial. To illustrate how the shift register can accomplish this, we will examine a typical circuit. Here we see a simple circuit consisting of a keyboard encoder circuit, 2 shift registers, and a decoder driver. Note that the first shift register, a parallel in, serial out, receives data from the keyboard encoder in parallel, then transfers the information in serial to the next shift register. This register is a serial in, parallel out device. The serial in, parallel out shift register receives the serial data, then transfers the information in parallel to the decoder driver device. To better understand how these registers were able to convert from parallel to serial, then vice versa, we will examine the register circuit. Here we see a circuit which is capable of serial in and either parallel out or serial out capabilities. Notice that this circuit consists primarily of clocked D flip-flops. When used as a serial in, serial out shift register, the parallel output lines Q1, Q2, and Q3 are absent. As was just mentioned, the serial in, parallel out shift register consists of a cascade chain of type D flip-flops that have their clock lines connected. The parallel outputs are labeled Q1, Q2, Q3, and Q4. If you recall the rules for type D flip-flops, the data can only be transferred from the input to the Q output when the clock input is high. Even if the input changes, the output will remain the same as long as the clock input line is low. Basically, the Q output retains the last valid data that was present before the clock pulse went low. Now let's examine the operation of this circuit as a serial in, serial out shift register. We will begin with a high followed by 3 lows at the serial in input. At the occurrence of the first clock pulse, the input line is high. This high clock signal causes the data to be transferred to the Q output of the first flip-flop. When the second clock pulse arrives, the flip-flop 2 will see a high at its data input, and flip-flop 1 will see a low at its data input. This causes the output of flip-flop 1 to go low, and the output of flip-flop 2 to go high. The third clock pulse results in a low at the data inputs of flip-flop 1 and 2, and a high at the data input of flip-flop 3. This results in the output of flip-flops 1 and 2 going low, and the output of flip-flop 3 to go high. And when the fourth clock pulse arrives, flip-flops 1, 2, and 3 will output a low, and flip-flop 4 will output a high. Notice that in the serial in, serial out shift register, that the single high condition was propagated through the entire shift register one stage at a time. However, most computers will use a parallel form of data entry since it is considerably faster than serial transmission. This is due to the fact that the information must ripple through the entire shift register in the serial in, serial out device. Here we see a parallel in, parallel out shift register. Notice that a common clock signal is used and that the input and output of each flip-flop is separated from one another. When the clock signal swings high, the information placed at each of the data inputs is transferred to the Q output of the device. As you can see, the process of transferring information is much faster using the parallel in, parallel out register as compared to the serial type device. There are a wide variety of shift registers available on today's market. We will examine only a few in this video. Here we see the SN7491A, which is a serial in, serial out 8-bit shift register utilizing transistor logic circuits. This IC contains 8 RS master-slave flip-flops with input gating and a common clock driver. This register is capable of storing and transferring data at clock rates up to 22 MHz while maintaining a typical noise immunity level of 1 volt. Power dissipation of this device is around 175 milliwatts with a fan-out of 10 from the outputs. The clock pulse inverter causes the circuit to shift information toward the output on the positive edge of an input clock pulse. This enables the shift register to be fully compatible with other edge-triggered synchronous functions. Also note that there are 2 inputs on this device labeled A and B. One is used for the serial data in, while the other is used as the input control. Here we see the SN7495, which is a 4-bit right shift, left shift register, which is capable of serial in, parallel out, or parallel in, parallel out modes of operation. The SN7495 is a transistor logic monolithic 4-bit shift register which uses 4 RS master-slave flip-flops with internal clock buffers and control gating for either right shift or left shift operation. When the mode control input is made low, it allows the serial in input to become active, and it also enables clock 1 for a right shift operation. Also, when the mode control input is made low and no data is being placed at the serial input, then the register will load the data at its parallel inputs labeled input A through input D. When the mode control input is made high, it enables clock 2 for the left shift mode of operation. Data transfer occurs on the negative transition of the clock pulse due to the inverters being placed at the clock inputs of the RS flip-flops. Here we see the SN74166, which is an 8-bit shift register capable of parallel in, serial out modes of operation. The shift load input is used to determine if the device is loading serial data or parallel data. When the shift load is high, the device works as a serial in, serial out register. And when the shift load is low, the device is being operated as a parallel in, serial out register. During the parallel loading operation, clocking is accomplished on the rising edge of the clock pulse through a 2-input NOR gate. The 2 inputs on the NOR gate are labeled clock and clock inhibit. To prevent false clocking, the clock inhibit input should be high only when the clock input is high. The SN74166 has a shift frequency of 35 MHz with a power dissipation of 360 milliwatts. We will now pause for a short review to reinforce the important concepts of the registers just discussed. All registers are basically a storage unit used to temporarily hold information until the information is requested by another part of the digital system. The most common storage register is the shift register. Shift registers are generally classified by the method in which the data inputs and outputs to and from the unit. The most common shift registers found are the serial in, serial out, serial in, parallel out, parallel in, parallel out, and parallel in, serial out. Shift registers may be used to convert serial data into parallel data, or to convert parallel data into serial data. The basic register is nothing more than a series of flip-flops configured to store multiple bits for future use. Shift registers are available in a wide assortment of sizes. Even though shift registers with 1024 bits are common, their basic operation will remain the same. This concludes review number 3. Next, we will examine some of the common displays found in digital circuits. The 7-segment light-emitting diode is one of the most widely used display devices found in counter circuits. This is due to its long life, low voltage requirements, ruggedness, and the fact that it can be plugged into an IC socket. The 7-segment LED has 8 PN junctions labeled A, B, C, D, E, F, G, and DP that emit light energy when forward biased. 7 of these junctions are used for decimal numbers 0 through 9, and 1 junction is used for the decimal point. The typical forward voltage for each segment is 1.2 volts, and the forward current limit is usually set at 20 milliamps. By turning on the appropriate LED segments, any of the decimal numbers can be displayed. For example, by activating segments B and C, the decimal number 1 is shown. By turning on segments A, B, D, F, and G, the decimal number 2 is displayed. Or by energizing segments A, B, C, D, and G, decimal number 3 can be displayed. To display decimal number 4, segments B, C, E, and G must be activated. Decimal number 5 is displayed when segments A, C, D, E, and G are turned on. Likewise, decimal number 6 is displayed when segments A, C, D, E, F, and G are energized. And decimal number 7 is displayed when segments A, B, and C are turned on. Decimal number 8 is displayed when all of the segments except DP are activated. And decimal 9 is displayed when segments A, B, C, E, and G are energized. We can also display the decimal 0 by turning on segments A, B, C, D, E, and F. The decimal point is energized when displaying more than 1 digit or when a number smaller than 1 must be shown. As you can see, by simply energizing the appropriate LED segments, any of the decimal digits 0 through 9 may be displayed using this simple device. The LCD, or liquid crystal display, is another popular 7-segment display device. Unlike the 7-segment LED display, the LCD segments do not generate light. Instead, they transmit or reflect light from external sources. As you shall see, there are 2 types of liquid crystal devices. These are the transmittive and reflective. Even though their operations are quite similar, there are major differences in their constructive techniques. The molecules in ordinary liquids normally have random orientations. However, in liquid crystals, the molecules are oriented in a definite crystal pattern when not activated. The liquid crystal will appear transparent. However, when an electric field is applied to the liquid crystal device, the molecules try to align themselves perpendicular to the electric field being applied. The charge carriers flowing through the liquid disrupt the molecular alignment, which creates a turbulence within the liquid. This molecular turbulence causes the external light to be scattered in all directions, which results in the activated area changing colors. This phenomenon is referred to as dynamic scattering. The liquid crystal cell consists of a layer of liquid crystal material made from such compounds as cholesterol nonanoate and p-azoxyzanosol, sandwiched between glass sheets with transparent electrodes deposited on the inside face of each glass sheet. When both glass sheets are transparent, the cell is known as a transmittive type cell. Whereas when only one glass sheet is transparent and the other sheet has a reflective coating, it is known as a reflective type cell. When not activated, the transmittive type cell simply transmits the rear or edge lighting through the cell in straight lines. In this condition, the cell will appear transparent. However, when activated, the incident light is diffused forward and the cell will appear quite bright, even under bright ambient light conditions. The reflective type cell operates from an external light source. When not activated, light is reflected in the usual way from the mirror surface, which causes the cell to appear transparent. However, when activated, the dynamic scattering phenomenon occurs and the cell will appear quite bright. As you can see, the primary difference between the transmittive type cell and the reflective type cell is in the method by which the light source is applied and in the construction of the device. The operation of the liquid crystal display is almost identical to that of the 7-segment LED display. By controlling the separate segments of the LCD device, it can be made to display decimal numbers 0 through 9. The recommended supply voltage for the LCD device is a 30-volt peak-to-peak 60 Hz square wave. The operating current is typically 125 microamps. The major advantage of the liquid crystal display is its obviously very low energy requirement. Another common display unit is the dot matrix display. The dot matrix display is a rectangular array of light-emitting diodes consisting of a 5x7 or a 7x9 pattern. The dot matrix display must be used with a character generator that selects the designated diodes to be activated at any one time to display any one of 64 characters. You will learn more about the character generator later in the video. Since the dot matrix display has a rectangular array of diodes, the display must be scanned one row and one column at a time to display a single character. To better understand how this display works, we will examine this simple circuit. In our example, we will illustrate the uppercase letter A. When the character generator scans the first row, the LED in column 3 will be high. Therefore, the LED in column 3, row 1, will be energized. Next, the character generator will scan row 2. As row 2 is being scanned, inputs on column 2 and column 4 will be brought high. This allows the LEDs in column 2 and 4, row 2, to become energized. The character generator next scans row 3. As row 3 is being scanned, columns C1 and C5 will become high. This allows these two LEDs to turn on. Next, row 4 will be scanned. When row 4 is scanned, inputs on columns C1 and C5 are brought high. This causes the LEDs at column 1 and column 5 in row 4 to illuminate. The character generator next scans row 5. When row 5 is scanned, inputs on columns 1, 2, 3, 4, and 5 are brought high, which results in these LEDs turning on. Next, row 6 is scanned. As row 6 is being scanned, inputs on column 1 and 5 are brought high. This allows these two diodes to turn on. The character generator next scans row 7. As row 7 is being scanned, a high is placed at inputs C1 and C5, which results in these two diodes being turned on. During this example, the rows were illuminated one at a time, since this is the system by which the character generator functions. However, the scan rate is so fast that all the LEDs in the unit appear to be activated at the same time. As you have seen, the individual LEDs are controlled by the inputs being placed at the row and column inputs. The dot matrix display has become popular due to its ability to display both alpha and numerical characters. The dot matrix unit also has the ability to display many other common symbols. Most character generators have the ability of providing 64 characters. The 64 characters displayed by the dot matrix unit are contained in a read-only memory, which is contained in the character generator IC. The forerunner of the 7-segment display was the Nixie tube. The Nixie tube is a gas-filled cold cathode vacuum tube which has 10 filaments inside, each shaped into the form of a decimal digit. The individual filaments are geometrically arranged within the tube to avoid masking each other. Therefore, when one numeral is illuminated, the other numerals are barely visible. As a voltage is applied between any single filament and the anode within the tube, the filament will turn on and glow a bright orange. Since the Nixie tube is a vacuum tube, it requires much higher voltages than does its solid-state counterpart, the 7-segment display. The Nixie tube requires a typical supply voltage of 100 volts. We will now pause for a short review of the most recent material discussed. The two most popular 7-segment display devices are the LED and the LCD. The 7-segment LED device emits light energy when the PN junctions are forward biased. The 7-segment LCD device, on the other hand, does not generate light, but rather transmits or reflects light from an external source. Another common display device is the dot matrix display. The dot matrix display is a rectangular array of light-emitting diodes consisting of a 5x7 or 7x9 pattern. The Nixie tube is a gas-filled cold cathode vacuum tube in which the filaments are formed into the shape of decimal numbers 0 through 9. Nixie tubes are no longer as popular as they once were. This concludes review number 4. Now that you have a basic understanding of how some of the common display devices work, we will next examine the circuits used to control these display devices. Before a display device can show a character, it must have a properly decoded signal being applied at its inputs. It must also have a device capable of supplying enough power to drive the display unit. This is generally accomplished with a decoder and driver circuit. These circuits may be individually packaged in their own IC, or they may be combined in a single IC package called a decoder driver circuit. Here you see a BCD to 7-segment decoder driver IC. These ICs are found in multimeters, counters, and other test equipment, commercial electronic scales, or wherever a numerical readout is required. Notice that the IC pin configuration is the same for the DM7446A, DM7447A, and the DM7448. The primary difference between these ICs is in their voltage and current requirements. Their operation, however, will remain the same. To better understand how the decoder driver IC works, we will examine this simple circuit. At this point, you should already be familiar with the operation of the counter circuit and the display device. As you can see, this counter circuit outputs a BCD code. When the counter circuit is at 0 counts, the BCD code of 0000 is fed into the inputs of the decoder driver IC. The decoder portion of the IC decodes the BCD input and causes the driver portion of the IC to output a high into outputs A, B, C, D, E, and F. This results in a 0 being displayed on the 7-segment display. When the counter IC increases by 1, the BCD code of 0001 is directed into the BCD inputs of the decoder driver. The decoder driver decodes the BCD input and causes outputs B and C to turn on. This results in the 7-segment display showing a numeral 1. As the counter IC further increases by another count, it outputs a BCD code of 0010 into the inputs of the decoder driver. The decoder driver decodes this input and produces a high output on pins A, B, D, F, and G. This results in the numeral 2 being displayed. As the counter IC increases by one more count, it outputs a BCD code of 0011, which is then fed into the inputs of the decoder driver device. The decoder driver decodes the BCD code and causes outputs A, B, C, D, and G to turn on. This results in the numeral 3 being displayed. When the counter IC increases by yet another count, it produces a BCD coded output of 0100. This BCD code is then decoded by the decoder driver IC, which causes B, C, E, and G to go high. When segments B, C, E, and G are illuminated, the numeral 4 will become displayed. By increasing the counter by another count, it produces a BCD output of 0101. This output is then directed into the BCD inputs of the decoder driver IC, where it is decoded and sent to the 7-segment display. The decoder driver device will cause outputs A, C, D, E, and G to energize, which causes the numeral 5 to be displayed. When the counter again increases by a count, it produces a BCD code of 0110. This BCD code is then fed into the decoder driver device. The decoder driver decodes the BCD code and causes outputs C, D, E, F, and G to go high, which results in the numeral 6 being displayed. As the counter IC once again is increased by 1, a BCD code of 0111 is computed into the decoder driver device. The decoder driver decodes the BCD code and outputs a high on A, B, and C. This results in the numeral 7 being displayed. By increasing the counter IC by yet another count, it causes the counter to output a BCD code of 1000. This output is then fed into the BCD inputs of the decoder driver IC, which causes the decoder driver to turn on outputs A, B, C, D, E, F, and G, and as a result, the numeral 8 is displayed. And by increasing the counter chip by one more count, it causes the counter IC to produce a BCD coded output of 1001. The 1001 is then directed into the BCD inputs of the decoder driver device, where it is decoded and fed into the 7-segment display. The decoder driver will turn on outputs A, B, C, E, and G. This causes the numeral 9 to become displayed. As you can see, by controlling the counter integrated circuit and using the decoder driver IC to decode the output from the counter and drive the 7-segment display, a simple circuit can be built which will count from 0 to 9. A circuit capable of counting higher than 9 may be designed by cascading a series of counter decoder driver ICs to any given length desired. In this simple circuit shown, the 50 kHz oscillator is fed into a divide by 50,000 counter. The 1-second pulses are then fed into a divide by 10 counter. The divide by 10 counter outputs a BCD code into a decoder driver IC, which is also used to drive a 7-segment display. When the first divide by 10 counter reaches 9, it resets back to 0 and outputs a pulse into the next divide by 10 counter. This pulse activates the second counter circuit and causes it to produce BCD coded outputs into its decoder driver circuit. The decoder driver IC causes the 7-segment display to show the divided down pulses in a numerical form. By simply adding more counter decoder driver 7-segment display devices, this circuit can be made to count to any desired length. It was mentioned earlier that a character generator was required to operate the dot matrix display. The character generator selects the specific diodes to be turned on by a method referred to as scanning. The character generator is generally a ROM device, which is programmed to output 64 characters from a 6-bit address input. ROM stands for read-only memory. The address inputs are labeled A1, A2, A3, A4, A5, and A6. A character code is fed into the address inputs, at which point the character generator is programmed to activate the designated column drivers and the row address at one time. As the character generator scans each row, it places new information on the column driver lines, which change from scan to scan. By changing the data supplied from the column driver outputs with each scan, various character combinations can be achieved. To better understand how the character generator works, we will examine this simple circuit. Notice that it consists of a character generator with the 6 character code address lines, as well as outputs for the row addresses and column addresses. Also shown is a 5x7 dot matrix display. We will begin by placing the code for the uppercase letter S on the character code address input lines. Notice that the character code for the letter S is 010011. This code is placed at code inputs A1 to A6. The program contained within the character generator will decode this input data and cause the character generator to select row 1 of the dot matrix display. At the same time, the LEDs in columns 2, 3, and 4 will become activated and turn on. Shortly after row 1 is scanned, row 2 will be scanned, and the data from the column outputs will change and turn on the LEDs in columns 1 and 5. Next, row 3 will be scanned, and the output going into column 2 of the dot matrix display is energized. This causes the diode at column 2, row 3 to turn on. Then the character generator scans row 4. As row 4 is scanned, the character generator will output a high into column 3, thereby turning on this LED. The character generator then scans row 5 and activates the column output for column C4. This allows the LED at C4 row 5 to turn on. Next, the character generator scans row 6 of the dot matrix display. It also outputs a high into column 1 and column 5 of the display. This forces both LEDs to illuminate. Then the character generator scans row 7 of the dot matrix display and at the same time activates the outputs for columns C2, C3, and C4. The character generator will continue to sequence for as long as the character must be displayed. The sequence, however, is so fast that the eye sees the character as being illuminated all at one time. Here you see the SN7441A, which is a BCD to decimal decoder Nixie tube driver shown with a Nixie tube. The BCD numbers to be decoded is applied at the 4 inputs labeled A, B, C, and D. This decoder driver operates much like the 7-segment device previously discussed, except that the SN7441A will only activate one output at a time. The outputs are designed to drive gas-filled Nixie display tubes. The output voltage of this device will typically be 70 volts with a supply current of 36 milliamps. When in operation, the correct filaments are energized, causing the neon gas around the filament to glow. This video has covered a variety of major subject matters. Knowledge of all this material is imperative if you are to be able to repair the high-tech equipment on today's market. Therefore, if you had difficulty understanding any of the material, it is recommended that you view this video as many times as necessary. Remember, the best jobs go to those who are best prepared.